So I hope you enjoyed that conversation and learned a lot from it. We're going to now move on to the final part of this week's module. So just to recap, we've talked about what is the climate, we've talked about what controls the climate, we've talked about the problem of detection, we've detected climate change, and we've talked about sort of the parameters that are changing and how it's both the mean value of the system but also the extremes that matter. And then in the conversation that we just had with Dr. Lynch and Dr. Fox-Kemper, we've talked about how we know that humans are causing climate change as opposed to natural factors. So for the last part of this module, what I want to talk a little bit about is what the future holds for us. And we're going to build on the conversation about climate models that we had and use those models to look into the future. Now that we know that those models are good enough to be useful, we can use them to think about alternative scenarios. What if we do this? What if we do that? What does the future hold? So we use these climate models to understand how our behaviors or our policies might influence our future. Now, moving through this relatively quickly, I want to talk a little bit about model projections for a few different parameters. I want to talk about what we can understand about what the temperature changes might look like under different scenarios, what rainfall changes might look like under different scenarios, how future warming will affect sea level. We have a lot of people living near the coast, and so sea level rise is a really important component of climate change. I want to talk a little bit about extreme events, and this could be extreme heat events or rainfall events, but extreme events in general. And then I want to talk a little bit about tipping points and what models can and can't tell us about tipping points. And we talked a little bit about this in the previous conversation, but I just want to come back and sort of highlight some key issues that arose in that conversation. So let's start with temperature and what climate models tell us about future temperature changes and how those might be influenced by our policy decisions. So what I'm showing you here is the latest IPCC projections for temperature changes relative to 1850 to 1900, so sort of after the Industrial Revolution, but not really deep into our carbon emissions. What you're seeing in black on the left-hand side of this graph are the actual temperature data going up through 2016, which is when the IPCC started these model simulations for the most recent assessment report. And what you're seeing in the colors moving forward in the future to 2100 are different pathways that Dr. Fox-Kemper was talking about, different pathways depending on what we do in terms of emissions. So you can see in this SSP 1.9 that you have a temperature rise that really doesn't cross 2 degrees, and most of the models agree that we wouldn't cross 2 degrees. And on the other end of the spectrum is sort of SSP 8.5, right, the sort of high emission scenario where warming gets up close to 5 degrees Celsius hotter than it was in the 1850 to 1900 period. So we talked about how these scenarios, there's uncertainty associated with the models. So if you run an individual model multiple times, you'll get some uncertainty there. If you compare one model to another, you'll get uncertainty there because the models don't perfectly agree. But by the time you get to the second half of this century, what you see is that the real uncertainty is in what we decide to do. Are we going to radically limit emissions quickly? And are we going to start pulling a lot of CO2 out of the air, albeit with technologies that don't yet exist at the scale that we need them to? Or are we going to continue to burn fossil fuels for decades, in which case, and large amounts of fossil fuels for decades, in which case we're more likely to track on the higher end of the warming scenario. There's another point that came up in the discussion that I really want to focus on here, which is that the atmosphere and the total amount of warming that we experience depends on the cumulative carbon emissions, not just on the annual emissions in any particular year. And so what this graph is showing you is the same data in a slightly different way. Again, the black is historical and the colors are future. But in this case, what we're showing on the y-axis is temperature rise, but what we're showing on the x-axis is the total amount of greenhouse gases emitted by humans over the 20th and then into the 21st century. So the black line shows the emissions we've had to date, or at least to date at the start of the IPCC process. Right? And that's about 2,300 billion tons of CO2. The blue band shows you how much more we can emit if we want to stay essentially below 2 degrees or closer to 1.5 degrees Celsius warming total. right? And in that case, we only have about 500 billion tons left, so only a little bit more relative to what we've already emitted. This is why it's important to begin emissions reductions quickly, because the atmosphere responds to total emissions, not just to the annual emissions in any given year. So if you look in the sort of warmer colors out at the SSP 8.5, for example, what you're seeing is we can emit quite a bit more carbon and still sort of stay in that temperature range, but we really need to limit our cumulative emissions, not just our annual emissions. So that's about temperature change. I also want to talk briefly about rainfall change. So models don't do as good a job on rainfall as they do on temperature, certainly for specific locations. But the general sort of paradigm that I want you to leave with from this section is that in a warming climate, in a changing world, wet places are likely to get wetter and dry places are likely to get drier. There's a really cool tool on the IPCC website, the link to it is on this slide, that allows you to put in a temperature change, like are we going to go up 1.5 degrees total, are we going to go up 4 degrees total, and look at changes in both precipitation and temperature across the planet. And so what I've taken here is a screenshot of a 1.5 degree future. And you can see that precipitation increases dramatically. That's sort of the blues and greens in the equatorial Pacific. The precipitation changes over North America are not particularly big in this scenario. But if we ramp up that warming to 4 degrees Celsius, so sort of the more extreme emission scenario, then you see really profound wetting of the wet places and really strong drying of the dry places, shown in sort of browns and yellows. But in general, while we do understand a little bit less about how precipitation is going to change in each place, we do have a really robust understanding that wet places are going to get more rainfall, they're going to get more extreme rainfall, and dry places are likely to get drier, and they're going to get more extreme droughts. Before I move on to sea level, I want to say one more thing about rainfall, and that is that it's not just rainfall that sets water availability. Temperature also matters. If you change the temperature in that system, you'll increase the amount that evaporates. And so actually, even a change in temperature will change the amount of water that's available for people and other organisms to use, because you're changing the amount that evaporates off the land surface rather than stays, for example, soaking into the soil or feeding into rivers. So now that we've talked about temperature and rainfall, I want to talk just a little bit about sea level. And this also came up in the conversation that we had earlier. What we do know is that global sea level has risen faster since 1900 than in any other prior century, at least for the last 3,000 years. To give you some sort of geologic context, the last ice age ended about 10,000 years ago, and so there was a big change in sea level as we came out of the ice age and ice melted off of the land and sort of poured back into the ocean. But we do have high confidence that sea level is rising now faster than it has in the last 3,000 years. And in addition to that, it's rising faster and faster. So the average rate of sea level change from up through the 1970s is slower than the average rate of sea level change from the 1970s to the early 2000s, and that's slower still than the most recent period that we have data for. So the rate of change of sea level is accelerating. Now, unlike atmospheric temperatures, we actually have very little ability to change sea level in the next, to slow the rate of sea level rise in the next 30 years. So the ocean is slow to respond. This is a conversation that, this is a topic that came up in the conversation that we had earlier. And so as a result, the ocean is still responding to the things we've already done. And so in this graph, what you can see, sea level rises now on the y-axis, time again on the x-axis, is that none of the different scenarios really have a big influence on sea level rise until the middle of the century. But what we do now has dramatic impacts in the second half of the century. Now, the second half of the century may seem like a long way away, but the infrastructure we build now will be in place in coming decades. Things don't come and go really quickly when it comes to infrastructure. And this sea level rise is a globally important phenomenon for a lot of people. So right now, almost 700 million people, and by 2050, closer to 1 billion people, live close to the coast, either on islands or in coastal cities, and those populations are growing. Coastal regions produce 15 or 14% of global economic activity. They have critical infrastructure, they're cultural heritage sites, and they face increasing exposure to storms that are associated with, that are more intense as a result of sea level rise, and therefore increasing vulnerability. And I really want to come back to this idea of infrastructure. We're going to talk a lot about this when we talk about solutions. A lot of the infrastructure that we build has a very long lifetime. That's true about power plants, it's true about dams, it's true about roads, it's true about cities. And so if sea level rise is going to continue throughout this century and beyond, the decisions we make today about limiting future sea level rise by reducing emissions now, or building infrastructure now that may or may not be vulnerable to that sea level rise, will be playing out for all of us in the coming decades. We talked again about extreme events, so I'm going to focus on this only very briefly, but I just want to key you back into this idea that a small change in the mean may in fact cause a big change in the frequency of extreme events. And I'll just give you one example among many, many, many. This is from a paper, it's now about a decade old, that looked at the number of extreme heat events in the western United States and how that might change from the 2010s to the 2030s. So this is not a 2100 kind of thing. This is in the here and now. We're in the middle of this diagram. And what you see is that in the 2010s, extreme heat events are fairly rare. You have maybe one or two, or maybe three extreme heat events per decade. By the 2020s, you're having those events more commonly 4 or 5 times, particularly in the southwestern US. And by the next decade, by the 2030s, what were considered extreme heat events in the 20th century are now going to be happening every year, or nearly every year. So while sea level and oceans take a long time to respond, air temperatures and extreme heat events take a very short time to respond to the changes in greenhouse gases and other forcings that are driving the climate. Now, this is both a positive and a negative. It also means that those extreme air temperatures will respond if we are able to reduce the amount of greenhouse gases in the atmosphere more quickly than the ocean will respond. And lastly, I want to talk just very briefly about tipping points. And we talked again about this in the conversation earlier, but I want to focus on just a couple of ideas that came up there and then maybe expand on those a little bit. There are a number of sort of what we would call nonlinear events or nonlinear processes in the Earth system. And we have a pretty good understanding of some of them and a pretty bad understanding of others. So one I'm going to talk about right now is one that was really relevant and discussed a lot in scientific circles in the 2000s and in the 2010s, and was alluded to by Dr. Fox-Kemper, and that's the sort of ocean circulation. So on the left-hand side, you're seeing a picture of surface and deep water circulation in the Atlantic Ocean. And what you're seeing is the warming waters at the surface of the Atlantic are moving northward, conveying heat towards northern Europe, which is why, for example, England's climate is so much more mild than Alaska's climate, even though they're at the same latitude. It's because of those warm waters coming up. And as those warm waters come up, they cool and begin to sink and return, in the blue arrow, back flowing southward. And that ocean circulation is driven by differential heating of the ocean surface at the equator versus up towards the poles. Now, as the Greenland ice sheet begins to melt and pour fresh water into that system, and that water therefore is less salty, and the temperature is warmer, you get less sinking of that ocean water up in the northern part of the Atlantic. And so people have thought for a long time that this might possibly slow or even shut down the entire Earth circulation system. What we think now is that it's unlikely that the whole system will shut down, but that circulation will weaken. And as a result, there will be sort of dramatic climate changes in Northern Europe. But there are other tipping points that we know less about. So for example, in the Arctic, which is warming much faster than the rest of the planet, there's an enormous amount of carbon stored in dead organic material that is frozen in permafrost. This is permanently frozen soils. It's been there for thousands of years. And that permafrost is beginning to melt. I pulled a headline from the paper actually today that says scientists have confirmed that temperatures in Siberia were over 100 degrees Fahrenheit, which is record-breaking temperatures last summer. So this extreme warming in the far north has the potential to begin to melt that permafrost. And as that permafrost melts and the organic material that's frozen in it begins to decompose, that represents a feedback, a warming feedback that releases CO2 to the atmosphere as a result of that decomposition. Or if the chemical conditions are right, may actually release that carbon as methane as opposed to CO2, and methane is a very strong, even stronger greenhouse gas, as we'll come back to in a future module. So at some point, the Earth may get warm enough that that permafrost carbon is released to the atmosphere, which causes further warming, which then makes more permafrost melt, which causes further warming. We call this in science a positive feedback, which is not a super great term because in society, positive feedback is a good thing. In science, a positive feedback is a self-reinforcing feedback. Another one you can think about is Arctic sea ice. So when the North Pole is covered mostly in ice, the sunlight that comes in is reflected by the white surface. And you heard Dr. Lynch talking quite a bit about the sort of complexity of light interaction with that surface. But in general, sea ice is relatively white, and therefore it reflects a relatively large proportion of incoming sunlight. As that ice begins to melt, what is exposed below is blue water. And that blue water is much more absorptive of heat than is the white ice floating on top of it. So now what's happening is instead of having most of that sunlight reflected away, you have more of that sunlight absorbed by the blue ocean, which of course warms the ocean, which makes more ice melt, which then of course makes the surface less reflective, which then warms the ocean more. Another positive feedback. So there are tipping points in the Earth system, nonlinear changes, where it's not just that you push the system and it moves, and you push the system and it moves the same amount, but that you can sometimes push a system for a long time and very little happens. And then you reach a tipping point and you actually go to a different steady state, a different stable state. And there are a bunch of these feedbacks in the Earth system that we don't understand as well as ocean circulation, but which may play a role. And it's very difficult to validate model results about these kind of rare tipping point events. So it's something out there that, I guess we could say is another thing to be concerned about, and modelers are trying their best to figure out exactly sort of how worried we should be. But this is a level of uncertainty in the models that we sort of have to live with just because we don't have as much data or understanding about where those tipping points are. So we're at the end of this module, and I just want to make sure that you leave this module with an understanding of what is the climate, what controls the climate, how we know that the climate is changing, how we know that climate change is a result of human activities and not some natural phenomenon. And finally, that our future very much depends on the solutions that we implement. So now that we've gone through this module and sort of defined the problem, we're going to take next week to look into sort of the sources of greenhouse gas emissions and trying to understand the kinds of policies and the kinds of ways of thinking about reducing those sources. And then we'll move into specific sectors and speak to content experts from vastly different disciplines to think about how you might leverage their ways of thinking about solutions to solve a particular piece of this puzzle. So I'll see you in class, and then we'll go from there.